All right, let's pull back the curtain on one of the most brilliant and honestly completely invisible pieces of tech that makes your computer work: virtual memory. It is the silent hero that makes modern multitasking in Windows even possible. It's the engine humming away in the background every single second. So let's just dive right in.
Seriously, have you ever stopped to think about that? You've got a game running, a browser with like 20 tabs open, your music player, a chat app, all at the same time? How do they all share your computer's RAM without just turning into a total digital demolition derby? Well, the answer is a masterful, beautiful illusion.
Here's the trick. Windows gives every single application its own private, protected virtual address space. You can think of it as its own private universe. From the app's point of view, it has all the memory in your computer all to itself. This vast, empty landscape starting at address 0 and going up for terabytes. And this isolation, this is absolutely crucial. It means a bug in one program can't just accidentally scribble over the memory of another one.
So how does an application actually stake its claim in this massive virtual universe? It's not like it just grabs all the memory it needs at once. Nope, it's a really clever two-step process, and getting this is key to understanding how Windows manages your resources so efficiently.
Okay, step one is reserving memory. Now, this is kind of like going to a land office and just pointing at a huge plot of land on a map. You're just putting up a sign that says, hey, this space is for me. No physical resources are used yet. We're not talking RAM, not disk space. It's just a promise, a placeholder in that virtual address space.
And then comes step 2, committing memory. This is where you actually start building on the land you claimed. When a process commits memory, the operating system makes a guarantee that it will be backed by physical storage, either your super-fast RAM or, if needed, the page file on your hard drive. It's only at this point that the memory becomes real and usable by the application.
And you know, the real kicker here is the difference in cost. Reserving address space, it's basically free, but committing it, that's what actually eats up your system's real resources. This is what adds to the commit charge you might have seen in Task Manager. It's the total amount of memory the OS has promised to all running apps. This whole two-step dance lets apps plan ahead without hoarding physical memory until they absolutely have to. Okay, so every app has its own fake, virtual address map. But sooner or later, the CPU needs to access a real physical spot on a RAM chip. So how does it get from the illusion to the reality? This, my friends, is where the real magic happens, through a lightning-fast process that's actually baked right into the hardware. So you see, a 64-bit virtual address isn't just one huge number. It's actually a set of directions. Think of it like a giant multi-level filing system. The first part of the address points you to the right cabinet. The next part points to the right drawer in that cabinet, the next part to the right folder in that drawer, and the very last part tells you which byte to read inside that folder.
So what does this journey look like in action? Well, when the CPU gets a virtual address, it uses those little indexes we just saw, the PDPT index, the page directory index, and so on, to literally walk through this hierarchy of tables. Each one points to the next until it finds the final page table entry, or PTE, and that entry holds the prize, the real physical address in RAM. But wait a minute, doing this multi-step lookup for every single memory access, wouldn't that be incredibly slow? Well, yes, it would be. The secret is a special piece of hardware called the Translation Look-Aside Buffer, or TLB. The TLB is a cache that remembers recent translations. So most of the time, the CPU doesn't need to walk the tables at all. The answer is already cached, making the translation happen at absolutely breathtaking speed.
We've seen how memory gets requested and how addresses get translated, but now we're facing another huge task. With every app reserving and committing millions of little memory ranges, Windows needs a way to keep track of it all, for every single process.
I mean, this is a massive bookkeeping challenge, right? You can't just scan a 256 terabyte address space every time an app asks for memory. You need a much smarter and more efficient way to manage the map.
And the solution is really elegant. It's called the Virtual Address Descriptor Tree, or VAD tree. For each process, Windows keeps this self-balancing binary tree. Just think of it as the master property deed registry for that process's entire virtual universe. Each little node in the tree describes a continuous range of virtual addresses, keeping perfect track of what's happening in that part of the map.
And each VAD is just packed with crucial information. It knows the start and end of the address range it covers. It knows if the memory is private to that process or if it's shared, like a common system DLL. And critically, it stores the protection rules. Can this memory be read from, written to, or executed as code? This VAD tree is the kernel's absolute source of truth for managing all of this.
So we've gone pretty deep into the mechanics of VADs and page tables. But why should you care? Because this entire complex system is what gives you a stable, secure, and efficient computer experience every single day. First and foremost, process isolation. Because every app is living in its own virtual universe, its own protected bubble. A crashing video game can't reach out and mess with the memory of your web browser or your operating system. This is the fundamental reason your whole PC doesn't just blue screen when one program has a total meltdown. Second, it's all about efficiency. Think about a common system file, something like kernel32.dll. Dozens of your running programs needed. Instead of loading a separate copy into RAM for each one, virtual memory lets the OS load it just once into physical memory, and then it maps that same physical memory into the virtual space of every process that needs it. This saves a huge amount of RAM.
And ultimately, it all comes back to building a resilient system. The Virtual Memory Manager is a core pillar of that, making sure that even when one app fails miserably, the system as a whole just keeps on chugging along.
So let me leave you with a final thought here. If every app's virtual universe is practically infinite, what's the actual bottleneck? What's the real limit? Well, it isn't the virtual addresses themselves. It's the physical resources, your RAM and your page file, that are needed to actually back them up. The true limit is the system's commit charge. When you run out of that, you are truly, completely out of memory.
If you want to help me out, please smash that like button, leave a random comment, and subscribe if you want to become a better hacker.